We're going to take a look at a static and kinetic friction problem now that is typical of something you might see. An 8.2 kilogram box of toys is pushed across the floor. It takes 48 newtons of force to get the sled moving and 35 newtons of the force to keep it moving at a constant speed. And we want to know first what is the coefficient of static and kinetic friction between the box and the floor. So the first thing I'm going to do will, of course, be to draw a free body diagram. Label all of these forces. 8.2 kilograms. Downward force of gravity, upward force is normal force. Those are the only two vertical forces, so I know in this case that mg is equal to normal force. And I may as well label what that value is. That's 80.4 newtons, which makes the normal force 80.4 newtons as well. So I apply a force, which I'll just call a pushing force, and opposing that is friction. I'm not sure what the exact relative amounts are, but I'll draw them as reasonably similar. So I look at what I'm given here. It takes 48 newtons of force to get the sled moving, which means that is how much force I need to overcome in order to get the object moving. And if it's just getting it moving, then I can assume a very small acceleration. So if I look at the net force equation, helping forces minus hindering forces equals ma. Then I've got my pulling force minus friction equals ma. And I'm going to say ma is effectively 0. So my pulling force equals friction. And that is going to be just overcoming movement. That's the coefficient of static friction times normal force. So I have the normal force, I have the pulling force. The coefficient of static friction then will be that pulling force divided by normal force. And that is, how much was it taking? 48 newtons divided by 80.4 newtons. And I get the coefficient of 0.597, I'll call it 0.6. Now the equation, that was part A. The equation that I would use to work out the kinetic friction will be very similar. And it says I'm going to keep it moving at a constant speed, which means the acceleration is 0 again. I'm going to use all of these same steps. F net equals ma, helping minus hindering is ma. So the pulling force in this case is equal to the coefficient of kinetic friction. So mu k is equal to the pulling force divided by normal force. The only difference really here is that I have a smaller pulling force. It is only 35 newtons divided by the 80.4 newtons of normal force. And that will be equal to, wait for it, 0.44. Next, we're looking to see how much friction force would be present if I pushed with a force of 25 newtons. This is a slightly deeper conceptual sort of problem. If I make Fp equal to 25. So I'm not going to jump right into equations. I want to think about what's happening here. The equation for static friction, force of friction static is, oops, I'm sorry, I messed that up. Is going to exist as a range of anywhere from 0 up to some particular number. So when I plug the coefficient of static friction in here, that gives me a maximum value of what the static friction could be. Oh, I'm writing that again. So that is 0.6 times the normal force, which was 80.4. And we should know that should already be 48 newtons. So is that how much force I have? If that were the case, I would have 48 newtons of friction and only 25 newtons of pushing force, which doesn't make sense. That would imply that friction is pushing the object and causing its motion. And that's just not the way that friction behaves. So the way I can think of this is I have up to 48 newtons available of static friction. I only need 25 to keep the object from moving. Is that right? Yes, 25 newtons. And do I have that much available? Yes, I do. So the object will not move. And in that case, the pulling force will still have to be equal to the force of friction, and that means force of friction is 25 newtons. And then I look at D. How much force would be needed to pull the box with an acceleration of 0.8 meters per second? So if I'm pulling it and it's accelerating, that would imply I must be dealing with kinetic friction. So my pulling force minus the force of friction that is kinetic equals ma. And what I'm looking for is this pulling force equals ma plus, now I'm going to write that as mu times normal force. So my pulling force then is the mass, 8.2, times my acceleration of 0.8, plus the coefficient of kinetic friction, which we found out here is 0.44 times the normal force, 80.4. And this is 6.56 plus 35. My pulling force then would have to be equal to 41.56 newtons.